Hello, everyone, and thank you so much for joining my session about building reliable AI agents using domain modeling with Koog framework in Java. And I'm really excited because we are about to share something truly special with all of you, with the whole Java community. But first, let me introduce myself as a speaker. So my name is Vadim Briliantov. I am a founding technical lead of Koog framework in JetBrains. I've been with the company for more than 8 years. And well, for some reason, the company is sending me to speak at different international conferences. No idea why. But in my spare time, I'm enjoying my coffee. Well, really, seriously, I love to drink coffee and I love to make coffee. And well, while for many people, making a coffee is just very simple, straightforward process. They click a button and get the instant result, and then they are happy. Look at this boy, he's happy. But I'm not. I'm not happy. I'm a developer. And for me, the process of making coffee is the constant fight every morning for the perfectly reliable taste that I can enjoy. And for that, I use tools. Really, I love using these pieces of machinery, pieces of engineering in the pipeline, and that's when I'm getting happy. And what is cool is that, I love when engineers, the amazing minds, the brilliant minds, get excited about weird problems and come up with even more weird solutions. For example, even the way you put your coffee in a portafilter before making it can end you up with very unreliable taste. You can get under-extracted or over-extracted coffee. So randomness is the main enemy of a good coffee cup. And well, no worries. Pretty recently they made a pretty weird solution you can enjoy looking at how it works. It's called Coffee Stirrer. And it makes sure that your coffee ends up perfectly uniformly put into a cup. Just look at this. Yeah, pretty weird. And I'm also crazy. I'm using it every morning before I make coffee, and that makes me happy. But well, to make a reliably good coffee, it's not only about using precise tools. It also is about using precise recipe. And I have my book where I put recipes for different sorts of coffee that I like. But if I want to share it with Java developers, for example, what I would do is I would define a record class where I will put all my parameters, because this is the best way to share the information. So now if you ask me what is my favorite coffee recipe, here it is. It's just the instance of this data class. And just by looking at it, I'm already feeling happy because I know what exact taste I will get at the end. But you may wonder, what's in it with AI agents? What's the connection? No worries, I will explain. So surprisingly, there is very much similarity about when you build reliable AI agents and when you cook reliably good coffee every morning. So let me illustrate that. So basically, what is AI agent? AI agent is a 3-component system which consists of the agent itself, the environment, and the models, one or many. So from the user's perspective, the process is very straightforward, same as with the instant coffee. The user will just click a button, send a request, and get back the final response, and then the user is happy. That's fine. But under the hood, there is the whole process that is happening. So the agent will send LM requests to the model and get back the LM responses, which are always either plain text, as instant messages, or tool calls. If the model decides to call a tool, the agent's logic will call a tool from the environment and come back with the tool result. And this process will continue until the strategy that is powering the agent's logic will decide to finish. And that's when the user will get the final result. So just let's think about this. If you are, as Java engineers, if you decide to build your own AI agents, what will be the environment for you? Any ideas? The environment is your Java application. So essentially, the agent will be ruling and orchestrating tools inside your Java app. Now let's talk about snakes. Anyone afraid of snakes here? Yeah? That's great. So if someone tells you that just because it's AI, it means that some Python-based AI agent should rule and orchestrate your Java application, well, don't listen to them. I have something better for you. As a coffee enthusiast, I have the original Java beans. Pretty great coffee. So jokes aside, if you're enterprise and if your enterprise lives on the JVM and you're developing in Java and someone asks you to develop an AI agent, then Java is already the answer for that. And that's, by the way, the problem that we faced in JetBrains 1.5 or 2 years ago. And that's why we built Koog, the open source AI agent framework that allows you to build your own AI agents natively on the JVM. And for us as an enterprise, the obvious focus was, of course, the enterprise. So we wanted our agents to be scalable, fault-tolerant, enterprise-ready, reliable, observable, and even cost-optimized. So Koog comes with the solutions for all of that. And importantly, Koog wasn't built as just a funny experiment. It was built out of necessity. So it was powering our own AI agent development inside JetBrains, our own AI products. And we faced lots of problems in the real world when we scaled these agents for millions of users. And then we developed the solutions for them. And then we packed the solution into a framework, and now it's available for the whole community because it's open source. And Koog is actually not really new. It was released almost a year ago. It's gained targeting JVM at the time. And it's gained almost 4,000 stars on GitHub, and it's not only used by JetBrains. For example, if you prefer reliable cars, the companies that make them prefer reliable agents, and they use Koog frameworks. So as banks, analytic platforms, and some of the largest companies in the world. And today is a very special day for Koog. Today we are launching the Koog for Java. So now you can build AI agents with Koog natively with Java. So let me show you how to do that. Remember this diagram on the left? Let's build this agent using Koog. So for that, I'm going to use the pretty familiar, for Java developers, the builder pattern. I will use AI agent.builder. And the first thing that I would do is I will register the tools from my Java application. Then I will also optionally provide a custom strategy for the agent so that the logic will be reliable. I will show it later. Then I will have to configure my agent to work with a specific model, to execute specific prompt, and with some other parameters. That will control the agent's behavior. And last but not least, I have to obviously connect the agent to the models, one or many. Here I'm connecting it to OpenAI. You can also use local models like Ollama or any others. And now, with this initial knowledge, let's help someone. Well, honestly, as a coffee enthusiast, I always, sometimes feel sorry about people who work in dynamic or busy environments. Sometimes and most of the time, they have to develop something really fast. And in some cases, they don't have enough time in the morning to cook perfect cup of coffee. They end up drinking an instant one. So let's help banking backend developers to automate some of the user features so that they will save some time for making a proper coffee. So let's build the agent for the banking backend. So how to do that in Koog? Well, pretty simple. I use AI agent.builder, register the tools from my banking application. I will show it later. Specify the prompt, select the model, connect to, in this case, OpenAI, build. 1, 2, 3, 4 meaningful lines of code, and the banking application instantly becomes agentic. And moreover, you don't even need a strategy for the start, because Koog will use some out-of-the-box default strategy. And of course, this simple example is pretty primitive. It's not yet production ready. And I will show you how to iterate on that. And by the way, like many LLM and AI frameworks, they stop right there. So you're not able to customize this logic. You're not able to provide a strategy. But in Koog, you can do that. I will show it. But first, let's see how to use this agent. So in order to execute some user's problem, you just use agent.run. And for example, the user is asking to send $100 to Mike. So what the agent will do, it will call different tools, like it will get the Mike's account, get the current balance, and send the money. So the user will be happy. Isn't that amazing, the world where we are living in? Of course, the agents, they don't just work in isolation. So let's, oh yeah, by the way, we forgot to develop tools. So we're developers. We want to develop something. Let's develop tools. So what are tools for the agent? The tools are essentially just Java methods that AI agent can call in order to solve the user's problem. So you as developers define the methods, and LLM will construct the arguments for them. So you can control the output and the logic, and the model will control the order of execution unless you provide a custom controllable strategy, which I will show it to you. So let's develop some tools in Java. I'll define a class communication tools. So how to say that this is a set of tools where, well, just inherit the marker interface toolset. And then inside, I'll define a method, send email. So of course, not all methods deserve to be tools. Not all methods needs to be exported to the LLM. So how to make it a tool? Well, pretty easy, just call it a tool. But now I have a question for you. Like, do you know what is the meaning of this string output? What does this send email return? What is the meaning of the method in general? Well, I don't know. Probably you don't know either. And moreover, the model will be also struggling to understand that. So optionally, you can also provide LLM descriptions for the model so that it will be more informed of the meaning of each method and each parameter. So now let's define more methods for our banking assistant. So I'll define a account read tools class. And first thing that I would do is I will inject the parameter user ID. If you want to provide some other tokens or other information, you also have to do that into a class. You don't want to expose that into for the model. So the user ID will be fixed, and the agent will be able to work only with the user that is currently authorized in the system. And now let's define the tools. Get latest transactions, get account balance, read account info. I'm not providing the implementations because I believe that you all know how to implement these methods. So let's focus on the declarations. But well, so the agent is currently able to communicate with the user and to read something from the database. But that's boring. That's not interesting enough. We don't want to build just yet another talking to user chat support bot, right? We need to build an agent that is actually proactive, that can solve the problem, that can do something for the user. So let's build account write tools. In the same way, the agent will be able to initiate a dispute about the transaction, or cancel the transaction, or transfer money. And you can build any other tools of your own for your specific application. So far, our agent is able to talk to user, read from the database, and write to the database. But as I already said before, agents don't just work in an isolation. You have to integrate into some backend. For example, if you're using Spring, Koog comes with out-of-the-box Spring Boot integration. So what you have to do is you open your Spring YAML config. You can configure the agents to work with a specific set of models. You provide the keys, and then you can define your agent service, which will have the access to multi-LLM prompt executor from Koog, injected or auto-wired from the config. As simple as that. And then you can define a function that will launch the support agent for the specific user session with a specific user problem. We just create an agent as we did before, and then you run it. And by the way, notice there is a second optional parameter into the agent run function, which is called user session ID, or user ID, or session ID, whatever you call it. So the idea is that if you run the agent multiple times, it will have the access to the user session. It will know you can run agent for multiple users in parallel. Now let's define the API method. It will be a /support endpoint, which will get the principal for authorizing the user and the user's request. So what we will do is we will launch the support agent using our agent service, and come back to the user with a reply once the agent is ready. But what if the user decides to come back? What if the user decides to continue the previously finished conversation? What if the user calls the same endpoint again? Of course, the user expects the agent to remember anything from the past. But the good thing is AI agent is not single use. So you can run the agent for the same user session multiple times. And in order to ensure that the agent remembers and stores the conversation in a specific place, you have to use the chat memory feature from Koog. So how to do it? Remember, we had the agent builder. You can actually install or inject different features from Koog into any agent. For example, here I'm installing the chat memory feature. And then I'm configuring it to work with a specific history provider, like where it stores the history. And of course, I don't want my agent to over-pollute the history with too much data. And that's why I'm also specifying the window size. So it will only save like the last 50 messages from the past. And of course, there is like a filter interface. If you want, you can also implement any filter for your messages. So you can control what messages will be stored. And then you build. So, by the way, chat history provider is pretty simple interface, just two methods, store and load. But you don't really need to even implement that, because Koog comes with out-of-the-box integrations for most of the popular databases. For example, if you're using Postgres via JDBC, only thing that you need is you provide your data source and the table name. And then it will save the sessions for each user together with the history that was before. And now let's use it. Let's see how it looks in action. So imagine that I'm coming to my agent and I'm asking it to send $100 to Mike, who is my friend. And it says, sorry, I failed. Then I come back to the same agent again, and I ask just one question. Why? What has gone wrong? And it says, oh, because you only have $99. Shall I proceed with like smaller amount? And I come back to the same endpoint again, which again runs the same agent for my user session. And I say, yeah, $20, please. And it says, oh, sure. Send $20 to Mike. The new balance is 79.9. So that's how it works in action. So the agent can remember the previous conversations. But that's not powerful enough. That's not controllable enough. Let's analyze how our agent behaves. So remember, we had several tools, conversation tools, database reads, database writes, all available at once for the agent. And that is the problem. Because in your system, currently, LLM rules everything. It controls all the operations. Do you see any problems? Any ideas?
It's non-deterministic.
Non-deterministic, exactly. So essentially, when you give too much control over your system to these randomly working guessing machines, which LLMs are, your system will be messed up. And that's something, even like with the best and most precise models, even like there is the 1% or 0.1% chance, this is something that enterprises cannot tolerate. And the problem is here. It's in the default strategy. And again, I mentioned it before. This is most of the agents, they just end up here. And most of the framework only allow you to define this kind of agent, very simple ones that just work in a loop. They're not controllable. But when developing our own agent, we realized that, well, that's not controllable enough. We cannot proceed with that. So by the way, if you want to code this default strategy, this is how it works. This is the code for like in Koog, and this is something you can develop by yourself. It's basically just a simple while-true loop. You're asking the model until it decides to send an assistant message instead of tool calls. Otherwise, you are still calling the tools. So this is, again, how it looks. And let's just talk about some problems. The first obvious one is all tools are available at once. So you're giving too much freedom of choice for the model. It can do anything, and it kind of just gets distracted by too much freedom at once. Second problem is that there are no guardrails. Nothing is tailored for your specific system. And even if you try to put some guardrails, the most natural for most of ML engineers to do that will be just providing a textual prompt, explaining what you want in a textual format. So you can provide some environments, but they are not. You can just hope that LLM will not forget some of them. So let's solve this problem with a custom strategy, and let's use domain modeling as a superior approach compared to naive prompting. So for that, let me introduce you this component. It's called subtask. And I'm saying subtask. It's not really sub-agent, although it works like a sub-agent. So subtask is an agentic loop of its own, which is focused on a specific part of the problem. It has access to only a limited subset of tools. It has a strictly typed input type, and it has a strictly typed output data class. So essentially, the subtask also has the access to all the previous conversations. So it's not working as independent agent. It's like a part of existing agent. And then you can stack this subtasks one after each other. So let me put it this way. So you can describe the expected output, like what you want from the model, as a type-safe class or Java record, plain Java object, instead of textual prompt. So, of course, someone might say that, well, you can describe how you spent the last winter and what you expect to be achieved by the next summer. But what you are left with in your hands is just hope. In a contrast, what you can do is you can require the model to fill in the form, to fill in the strictly type fields of a Java class. And for that, of course, like the Java class has to be serializable, and you can also provide the same LLM descriptions to make the model aware of what is the meaning of each field. And then how it works, the model will work hard and call tools in a loop until all the fields are resolved. It will not be able to proceed further before everything is resolved for the specified data class. If you think of an analogy in the real world, imagine that you are coming to a bank and you are asking for a loan. You cannot impress the bank manager with your oratory skills. You cannot talk your way into getting a loan. You have to bring the passport, the birth certificate, the salary certificate, some other documents, and you have to fill in the strict form. And only then you will be able to proceed to the next step of getting a loan. And even if you try to break through the process, the security guard will probably stop you. And that's essentially what Koog is ensuring. It's like a security guard. It makes sure that the model cannot proceed to the next subtask before everything is resolved, before the form is fulfilled. So, to sum it up, naive prompting gives you hope. Domain modeling gives you a contract that you can trust. So let's build a custom strategy for our banking support assistant using domain modeling. So we're going to start with a string node of the strategy, which will has the request from the user. And then we're going to focus our agent to identifying the problem, what was wrong with the account. And we're going to focus our agent to work only with conversation tools and reading tools. No writing operations are allowed. And we're explicitly requesting the model to come up with the account issue summary in the form of a data class. And you can specify all the fields that you want to be resolved until you can proceed further. And then what we'll do next, of course, we're going to fix the problem. So the fix problem step will take the account issue summary. Of course, I can connect the steps only if they are type compatible. And this part will be focused on the reading tools and writing tools. No conversation is allowed. And I'm requesting the model to come up with the account issue solution, which is another record class, plain Java object. So, so far we identified the problem and fixed the problem. Are you happy? I'm not. Because as a developer, I want to verify everything. So let's add verification step, which will take the account issue solution, and it will provide a critic result, which is a class from the Koog framework, which has the marker whether verification has passed, if it's successful or not. The string feedback, which is optional. If something went wrong, that will be the description what has to be improved in the solution, and the original input to pass through. And this step will be focused on talking to user again and reading from the database. So then we can actually branch depending whether successful is true or not. If successful is true, we are passing the account issue solution to the finish step, and we finish the agent. If successful is false, we are passing the string feedback to the adjustment step, which then comes back with the account issue solution. And this loop continues again and again and again until verification step is happy. This strategy is much more reliable, much more focused, and much more controllable compared to anything that we built before. Same way as with coffee. Tools alone, no matter how precise they are, cannot guarantee the outcome. You also need the right recipe, the right strategy that will rule what is happening. But I'm a developer. I want to code that. So let's do it. The main important thing here is to understand how to code the basic component, the subtask. So for that, again, the same legendary builder pattern. I call AI agent subgraph because it's not like a single node in a graph. It's like a whole subgraph with a loop. AI agent subgraph.builder. I provide the input class, the output class, set the limited set of tools, provide the task, which is the textual question, like what I want my model to do. Optionally, I can also switch the model on a fly for this specific step. And finally, build. As simple as that. And now, I think we can actually proceed with building our strategy. So identify problem will look like this. AI agent subgraph builder with input string, with output account issue summary, limited tools, communication, and reading. With the task, identify the user problem, blah, blah, blah. You can formulate the question as you like. And in this step, because we are going to do lots of conversation, I prefer using some GPT model because, in my experience, it works a little bit better with the conversation. The next step is fixing the problem. Same thing, same pattern, different types, different request type, different tools, different task, and also I provide different model here. I prefer using some Sonnet from Anthropic because, again, in my experience, it works a little bit more precise with the tool calling. Verify solution step is almost like that, different parameters, different types, but instead of requesting the model to provide me some output class to fill in the form, I'm requesting it to do the verification. So I do the with verification here, and it makes sure that it returns me a critical result from my input. And finally, the adjustment node, the adjustment step in the strategy. Same thing, different parameters, different question, and again, a different model. What's left? Well, of course, I need to glue all of that together. And for that, I use AI agent graph strategy.builder with some input class, the string, and with output class account issue solution. That's the final output for the whole strategy. So I need to now connect my steps using edges, these ones. So I go from node start to identifying problem, then to fixing problem, then to verifying solution, and then I have to branch. And for that, again, I use the builder pattern. I can provide AI agent edge.builder. From verify solution, we go to adjustment step, and then I can program the condition as a type-safe lambda. Everything is type-safe here. So if verification is not successful, then I will go to adjustment. But currently, if you try to write build, you will not be able to. Why? Because verify solution provides you with the critic result class. And adjustment step, remember, it requires a string feedback. So these two types are not compatible. So you need to do some like type transformation. And only then you will be able to build the edge. So I write transformed, and I get the feedback from the critic result. This is a field, the getter in Java. And now I can build my edge. So you have compile type checks for any chains that you do. You can only connect two nodes to subgraphs if they are type compatible with the input and the output. Same way I can build the other branch to finish. And then I connect the adjustment step and verify solution. And finally, I build my graph strategy. That's it. So Guido mentioned that I was mentioning some history or context management. Probably I haven't, right? And the reason is, sorry?
You talked about chat history.
Chat history, right. But when building the strategy, I didn't even mention that. And the reason is because Koog takes care of the context management out of the box. So it actually passes the history to the next step by its own. You don't have to even take care of that. Moreover, you can even switch models on the fly. So remember, each step is working with a different model. And what Koog does in this case, it re-explains the previous history from the past, from the previous model to the next one. And even if some tools become unavailable, we made these mistakes. Some models will break, especially the smaller ones, if some tools are not available anymore. And we also fixed this problem out of the box. You don't have to think about that. Tool calls from the past will be also re-explained the right way. So, of course, you're not just limited to autonomous subtasks or steps. You can even build your custom nodes, which are either actions that you can put anywhere in your strategy, or some guardrails that you can also build and put somewhere, tailored for your specific case that you are solving. So for that, you are using AI agent node.builder with the input class, with the output class, and then with the action, which is just a lambda or function that you can code in Java. And you can do anything like, for example, asking the user for some feedback and getting back the feedback and then providing it further to the agent. And then you build. So this is pretty much the main advantage of the graph strategies, because first you get the control, second you get the possibility to visualize that. And that's important because you can show the graph strategy of an agent even to an ML colleague who is not even familiar with JVM, not even mention Java. And they will be able to understand the graph and suggest some improvements. And they also did that, by the way. Another advantage is that graph strategies can be persistent. You cannot persist the Java code into some storage and then restore from where it stopped if some crash happened. But you can persist the exact node, the atomic step of execution, and then restart on another machine. And I will show you how to do that later. So these are probably main reasons why, for example, Mercedes-Benz used Koog for building this specific chat support agent. So how it's working is whenever you want to book a maintenance for your vehicle, you go to their support agent, which will follow the specific custom nodes. There is like very precise strategy of very custom nodes. And then only after you get the final confirmation from the user, then the maintenance will be booked. And also you can visualize and reason about what's happening. But again, it's not just about graphs. In Koog, we cover all modern approaches to building AI agents. Of course, you can always start with basic agent, the simple one, without any strategy. Then you can either use graph strategy or functional strategy, like you just implement a Java method, almost in plain Java code, still with access to most Koog features, but with some caveats. Then you can also build multi-agentic systems, or you can build planning agent using goal-oriented action planner. I will show it to you. So we are not focusing on just one approach because we realized when building something, there is no silver bullet in AI. There are different approaches that are perfect for different scenarios. And you have to be able to like switch between them. So the functional strategy is similar to the graph one with the one difference. You can prototype much faster. You don't have to think about graphs. You can model the behavior using for, if, while, and normal Java code. But you will lose the persistence. And you will have less observability because you don't have the access to like logical steps in the algorithm. It's just code. And also, you are not able to visualize that. But still, it's better for prototyping. And yet, you can build very powerful strategies with access to most of the Koog's capabilities. And that's how you do it. I'm not going to dive too deep into that because we don't have enough time for it. But generally speaking, you just use the same AI agent builder. And then instead of providing the graph strategy, you provide the functional strategy. And then inside, you just insert your code, what you want your agent to do. Then there is planning strategy approach. So what planner is, it's essentially something in between the functional and the graph. So essentially, you are providing kind of nodes of your graph strategy, but without the edges. So nodes are called actions, and each action has a precondition and side effect. And then instead of connecting one node after another, and providing the explicit transitions, what you do is you just provide the preconditions and side effects, and then the planner algorithm, which is called GoUp, goal-oriented action planner, it will decide in runtime what is the right path of execution. And of course, everything is type safe as well. So unlike the graph strategies, is not as much controllable. So you still have some randomness, which is still deterministic. It's not using LLM. But in some cases, it might find some paths that developer didn't think about in runtime, which is cool. And again, instead of providing the graph or functional strategy in a builder, you provide a planner strategy, which works with a specific data class, a specific plain Java object as a world state. And then you provide actions, goals, and so on. I'm not going to dive too deep into that. I'm just showing that you can do it, and there are some benefits. So far, we have built a reliable agent with a very precise graph strategy. What can be wrong? Well,
Let's say, because it seems like when you have like a graph strategy,
Yeah.
it's very rigid in manner. So if you basically have a prompt that wants to jump and like there's no edge going to that, like what will happen?
If there is no edge going to some step.
Yeah, because like let's say like there's like multiple steps
Yeah,
in
yeah,
your graph from within that particular node. There's no
Mhm.
edge. You wanted the prompt. You want to specify the prompt to go back to, let's say, the step
Yeah, yeah.
like.
Okay, sorry. Yeah, let's do the questions afterwards, but this one I'll answer. So if there is some hanging node in a graph, then you can also write, there is a test framework, sub-framework in Koog. You can just test that some nodes are reachable, and then you can ensure that before deploying your code. But yeah, talking about the problems. So essentially, even with the best strategy, LLMs take some time, and user conversations take even more time. So suddenly, for example, your application might crash, which is normal. That's fine. That happens. Or if you're using Amazon EC2 Spot instances for the obvious cost optimization reasons, at some point Amazon can preempt your process and rerun on another available machine. So you will essentially lose your progress. And then you will have to restart the agent again, pay again for the same tokens, which is, by the way, expensive. And also you will lose the progress. You might even end up in an inconsistent situation with a database. So that's probably not acceptable. But there is a solution, Koog's persistence feature. So how it works? Well, same as with chat memory, you just install the feature into an agent, any agent. But it has to be a graph agent specifically. And then you have to configure the feature to work with a specific storage, like where to store the checkpoints. And then you require the feature to automatically checkpoint every single atomic step inside your strategy. So what will happen? Let me illustrate that. We have this graph strategy, and then you're going to checkpoint the exact place where the agent stopped together with the agent step. So let me zoom in and zoom in again. Imagine that you are somewhere inside the verify solution step, somewhere in this atomic node inside the subgraph, which is, for example, sending LLM request. So before or after the node is it was executed, Koog will checkpoint the exact place in the algorithm, the exact node, as well as the message history and all the other types of meta information, which is overall the agent state. And then, after a crash, the same agent will recover from the failure, exactly where it stopped, not just with the same message history, but also from the exact place in a strategy. And to enable that, you just have to provide the storage. Again, storage provider is an interface, but if you're using some popular databases, you can just use out-of-the-box integrations for them, and you just start it to work with the persistent feature. That's it. So, did we miss anything? Well, of course, you cannot just code the agent and believe that it's going to be working. You have to also be able to debug and monitor in runtime and be on call for your system. And for that, we need to integrate with some observability tooling. Observability is also a feature. You can install it to any agent and then configure to work with any spawn exporters and spawn processors that you have in your OpenTelemetry tooling. Or, for example, there are pretty popular tools for AI observability specifically. And Koog comes with an integration with most of them. For example, if you're using Langfuse, you just add Langfuse exporter, provide the credential, and then open your Langfuse console where you can see the graph of execution of any agent, including the steps, nodes, tool calls, timings for every operation, tokens spent, and so on. You can reason about the execution. You can share it with the ML colleague, and they will help you to improve it. Or if you're using Weights and Biases Viv, the same thing. You can add Viv exporter, provide the credentials, and see the same information in the Viv console. In the future, we will also provide out-of-the-box support for Datadog and Dynatrace, but even now you can do that by your own with the span exporters. So, are there any other problems left to solve? Of course, once you scale the agent, the first problem that you're going to hit into, which, by the way, we did inside JetBrains when building our different coding agent, is that long-running AI agents are expensive. For example, like running a single iteration of SV benchmark costs like several hundreds of dollars. That's not cheap, right? And second problem is, aside from that, LLM will struggle with the long context over time. So whenever the agent is calling a tool and you're getting back the tool response and so on, you're having long message history, the agent, in order to make the next decision, it will have to read the whole book of what was before providing you with the next action, which is, first of all, it takes lots of time. Second of all, you are paying again for the same tokens from the beginning for the agent to analyze it. And third of all, at some point, especially if you're using small models, you will hit the context limit. And the model will just break with an exception. So, of course, we built a solution for that, which is called history compression, which is, by the way, in my understanding, pretty unique for Koog on the JVM. There is no other solution like that out of the box, as far as I know. So in order to use the history compression, it's again the node that you can put anywhere in your strategy. Use AI agent node.historyCompression, specify which inputs it works with. The output is the same because it only changes the underlying history. And then you build. And then you can put this history compression anywhere between two different steps. And you can also program what is the criteria for it to be executed, what is history too long for you. It's just a plain Java function, Java method that you can supply. But what will happen? It will essentially summarize the history into a TLDR, what has been done before. And then the agent will proceed with just this single message, which will be faster, more efficient, but then you're going to hit with the next problem. Now the message history is too small. The model is not informed enough to make the next decision. And we also faced this problem when evaluating our agents. And we built a next solution, which is strategies for history compression. History compression strategy is an interface, but we also came up with a few implementations out of the box. The first one that we did and we tried is chunking. So you can use it the same way as before. You just have to provide the history compression strategy here. And here I'm requesting the algorithm to chop the history into the pieces of 20 and then compress each of them independently. So that instead of reading the whole book, LM will be reading a plot of the conversation, which is proven by our benchmarks, working pretty much better than just a single message compression, but still not precise enough. Why? Because usually, if you as a human, as a developer, if you know what you're building, you also probably know what specific pieces of information will be important for the model. And we also face that. Sometimes the model just forgets important pieces of information. And for that, we also built a next strategy for the history compression, which is called fact retrieval. So you provide the new retrieve facts from history instance. And inside, you specify the concepts, like the facts, what will be important for your system to be kept in the history. Like the first concept that I will do for our banking assistant is the important steps that we did throughout the problem solution. And the second one is suspicious operations. If some operations that we were analyzing were suspicious, let's also keep them. And you can also think about any other pieces of information that are important for your system. And we actually used this strategy, and it brought us a 6 to 8% improvement on the benchmark, because it's much more precise. So it's a pretty complex algorithm that we actually fixed a few times with our ML engineers. We hit into problems, and we evaluated it. So how it's working is it's extracting the history, the pieces of information using the model, or you can also ask to work with another model, and biased one. And then we are rebuilding the plot of the conversation so that it naturally mentions the facts, and that's how it works the best. So you can actually don't even know about this because it's just working out of the box. You specify the concepts, and that's it. So this is the illustration how it works. So now instead of reading the whole book, LLM will be left with just a few important pieces of papers on the table. So if you want to observe the full example that we just cooked using the Koog framework, please feel free to visit this link. It goes to our GitHub with examples. And let's summarize. So you can start. Sure. Yeah, that's it?
Yeah, thank you.
Welcome. So you can start with a simple AI agent. Then you can program your tools in Java. Then you can connect optionally to your Spring backend, if you want. Then you can add sessions with chat memory so that the agent doesn't forget the past conversations. Then you can tailor type-safe strategies specifically for your use case, and you can select between graph strategies, functional strategies, or planner strategies so that you get the most reliability and control over the agent's logic. Then you can enable recovery from crashes using persistence, connect to observability tools to monitor what's happening in the system, And then finally, last but not least, you can cost optimize with history compression, as well as with many other tools that I didn't even mention during the talk. So, please feel free to visit our Koog website as well. And if you want to learn more, there is also a link to GitHub and to our documentation. And try Koog today, Koog your enterprise AI tomorrow. Please don't forget to go to our GitHub. Feel free to leave a star and watch. Thank you so much for your attention. And now I think we have around 5 minutes left. Please let me know if you have any questions. Yes, of course, Koog provides MCP integration. But of course, most of the time, if you are building agents right in your backend, it's usually the same process. So you can just call the tools natively. It's much faster. But if you have the necessity to call something from remote, you can use MCP, of course. Yeah, so if you want to check that the agent is allowed to use a tool with a given input, what you have to do, and that's pretty common request, by the way, what you have to do is, surprisingly, you just put the right guardrail in the tool implementation. So the first thing is you control what the tool is doing and what the tool is returning back to the model. So if you see that the tool is requested to run some operation that is not allowed, you just check that in your code of the tool, and then you respond with the right exception or problem description back to the model, and then it will retry or do something else. So you fully control that situation. That's so if we are talking about this specific example, read account information is allowed for the current user. So the user ID is not actually provided by the model. It was injected as like a separate parameter in a class. So we are working with the currently authorized user already. But again, if it was some different situation, you can do the check there in the code of your tool, and then return with like some description of a problem instead of the result. And then the model will know, and it will try some other approach or just say something else. Yeah, good question, thanks. So how does Koog compare to other AI agent frameworks, specifically on the JVM? So let's talk about Spring AI just as an example. So Spring AI, as well as basically LangChain4j, is an LLM framework. So it shines when it comes to LLM integrations and vector database integrations. So Koog also provides all of that, as well as it can be, it integrates with the Spring AI as well. So you can use Spring AI if you want in the background, like for connecting to models or to storage providers, and then you can use the orchestration logic from tools. So from Koog. So the focus of Koog is building a custom strategy, which is not available in Spring AI, for example, and then using all these solutions for the common problems that we face, like history compression or like message rewriting or fixing the tools for the small models, as well as persistence layer. So all of that is not the responsibility of LLM AI framework like Spring AI or LangChain4j mostly, but it's more of responsibility of a higher level framework like Koog. If you compare with Imbabel, for example, which is, by the way, another cool framework, it also provides you with the way to build custom strategies, but it's mostly focusing on GoUp, the planner agents. While Koog also provides GoUp, it also comes with functional and graph approaches, and also with persistence and history compression and all of that. So, of course, you can choose, depending on the problem, what types of agent you want to build. Can I paraphrase your question? So did I get it right that you're asking if you're able to build your own feature?
Not my own feature. Do you have generic hooks that I can basically inject
Yeah.
any other?
Yeah. So there is a event handler feature. So you can handle all the events like node beginning, LM call beginning, the output, and all of them, tool call. And also there is a pipeline, which is a lower level API. So you can also change the agent behavior. For example, currently, in the next release, we're going to provide the long-term memory and Amazon Bedrock agent core integration. So what it will do, it will first, before sending LM call, it will intercept this event, go to Bedrock or other long-term memory provider, augment the prompt, change it, send it to the model, come back, update the history. So you can actually control what is happening inside, and you can intercept the inner logic if you want. Does it answer your question?
Yes, 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 yes.
Yeah.
And that's the like under the hood. And you have used the same primitives for some of the things that you talked about here.
For all of them, yes.
Perfect.
All of the things are built on top of these primitives. Everything is extendable, and you can implement all of the interfaces and customize the agent's behavior. Yeah.
Related to that.
Yeah, good question. And I think it's going to be the last one because we are already a little bit out of time. So if you want to make sure that you are restarting your agent with the persistence and you are not using the history from the broken versions of your agent, you can also, first of all, implement your own storage, so you can control the logic. Or you can, if you are using Postgres, for example, you can use migrations there as well. So for example, the broken ones you can migrate to like nothing. Like you can just clear the rows or change a table name, for example, as well. So you can version that on the database level.